Now, after going through the first pass, okay, then you compute the error for each output node in this fashion. Okay. So this is like an ordinary error multiplied by a correction factor. Now you take that error, okay, and adjust the old weights. Now you're going to go backwards. The initial pass, we started from the left side, the input layer, and worked our way through to the output layer. So now we'll start from the output layer, compute the error, and then take part of the error. The error here is a correction factor, which is called the learning factor. So it's a constant between 0 and 1. It's also called weight decay parameter. So this will take part of the error, okay, and add it to the old weights, and that will be the new weights. So you go through the backward process from right to left and update all the weights. Okay, so let's see how we do that. The value of the node, the actual value of node, okay, so node 6 is they dislike the cheese, node 7 is like the cheese. So 6 value of y is 1, 1 meaning they dislike, 0 meaning they like. Number 7 is like. So 1 here would mean you like the cheese, 0 would mean you don't like the cheese. Actually only one node is enough. In a binary case, it's not necessary that you need to have one more, but you need the two nodes to be able to compute the output back into probabilities. Now y hat is the value of the probability, the value of the output value. So this is your, okay, so that's our y hat for node 6 and node 7. Okay. Now the error is the formula for error. Okay. So you have y hat times 1 minus y hat times y minus y hat.
I think y hat for node 7 is wrong, or just from the wrong thing.
Yeah. Y hat must be that. You're right. So now we have the errors, and assuming a learning factor of 0.5, okay. So now we have the weights coming into 6. So what are the weights coming into 6? The old weights are these. These are the old weights. And the way we update it is L times the error, and you add it to the, so here error for 6 is that. It's the same error for all of those weights, so it's just like that. Okay. So the new weight is the old weight plus L, okay, plus F4, make it absolute, and that error. So that's the new weight. Okay, so use the formula for Now what about node 7? Node 7, the old weights are these. Okay. And the error for 7 is that. Okay. And the new weights are the same formula from here, so you can copy that. So these are the three. Okay, there you go. What did I do? Oh, no, this is the error. Error is that, and I need to have the same error for the rest of them. Then I copy that formula down again. Now I have it. Okay. Okay, now so this is how you will update the weights for node 7. Okay. So now we have done node 6 and 7. Okay. Now we go to 3. You have to update the weights of 3. Okay. So node 3 to node 6 and 7. Node 3 to 6 and 7, the weights are these. So here we need to do a transpose. Or we can just simply do it this way. 6 and 7. So these are the two. Now the error for 6 is that, an error for 7. So now we take the weight and multiply by the error. And sum these two, you get the error for node 3. Okay. So once you have completed the weights, then you have to compute the error for each of the hidden nodes 3, 4, and 5. So that's our error for node 3. And similarly, we will work the error for node 4. So node 4 to node 6 and 7. Those two weights are node 4 to 6, and then this one is E25, and the errors are for node 6, the error is that, and node 7, the error is that. So you're finding a weighted average of the error to be propagated backwards to the previous node. So you multiply by the weights, like how we have done here. Okay. And then the sum of that. So that's the error for node 4. And you do the same thing for node 5. The weights are these, D26 and E26. And the errors are 6 and 7, the errors are these. And then weight times error, and sum that. So now we have the errors from 6 and 7, errors from 6 and 7 propagated backwards to 3, 4, and 5. And now we have to use those errors to adjust the weights coming into nodes 3, 4, and 5.